Hi, my name is Scott Burleigh. I work at the Jet Propulsion Lab, and I will not be talking about flight software development and simulation. I will be talking about something entirely different. This will be reporting a little bit on some architectural work in delay-tolerant networking. For those of us here who don't know anything about delay-tolerant networking, none of this will make any sense at all. So, this would be a good time to get coffee or something. But if you know something about DTN, then I hope this will have some interest. The problem that we're looking at here in this particular context is scalability. DTN is well defined by now. It's tested. It's operational on space station. We're going to be baselining it for PACE, for Gateway, for other missions. It's a CCSDS standard, and it's well on its way to being standardized within the IETF as an internet standard as well. The problem there is success. That as the scope of applications of DTN grows, the size of the networks is likely to grow. So how well is DTN going to scale up to these larger networks with more complex topologies? And there are sort of two general classes of obstacles to scalability for DTN. One is routing. Route computation in a delay-tolerant networking sort of takes two general paths. One is opportunistic routing, which is where you really don't have any idea what the topology of the network is. You just take your best guess and flood through the network and try to back off from flooding so you don't stress the network too much. And that's what all the many routing systems for opportunistic terrestrial delay-tolerant networking are based on, is essentially how do I not flood? How do I succeed without completely flooding the network? For spaceflight operations and for other environments in which we do know something about the topology, maybe and almost always a four-dimensional topology, that is, we know when there are going to be opportunities to transmit and when those opportunities will stop. For that sort of environment, we've been using for many years something called contact graph routing that charts paths through this four-dimensional contact topology, and that works well, but it is computation intensive. It's a lot of Dijkstra searches and so forth. It works fine, but for extremely large contact plans, the search time can be very long, and at some point it becomes untenable. So we need a mechanism by which the route calculation that you do at any single node is within some reasonable bounds, and that mechanism doesn't exist yet, and that's part of what I'll be talking about here. The other major sort of class of obstacles to scalability for delay-tolerant networking is that to enable DTN to work across a very broad range of operational scenarios and lots of different kinds of operational problems, you need a lot of knobs. You need a lot of things that you can tweak to adjust the way operations work for nodes in the network. And so the business of configuring a node in a delay-tolerant network so that it'll work properly with the rest of the network is pretty tedious. You need these kinds of information resources at every node. You need to know what are the protocols, the underlying protocols that you can use for point-to-point transmission, in the same way that in the internet you need to know whether you're using SONET or Ethernet or FDDI. You need to know the network topology, the four-dimensional network topology. When are the contacts going to arise? What are the limits on the transmission rates on those contacts? When are they going to stop? You need to know something about what the applications that they're going to be taking advantage of the capabilities of the node are going to need. What are the expectations that they're going to have of the service that the network is going to provide. And you really need, because this is really key, you need, for security in the network, you need to know encryption keys, security policy, potentially a lot of security configuration and tuning to make the operation of the network safe and reliable. So all that configuration currently is done using manual tools. There are mechanisms that we're developing in management protocols to make that work more efficiently than the prototypes that we've been using, but it's still heavily manual. If you, the internet analogy would be that if you had to have a network manager configure every computer and every phone that used the internet, pretty soon it would not work anymore. And the way that the internet got around this problem is by using something called, well, one way anyway, is using something called DHCP. And so the intent here is to come up with something that is roughly analogous to the way DHCP works in the internet. Very roughly, but analogous in the sense that it fosters that sort of scalability. So you can think of this D10 node auto configuration that I'll be talking about here as being very roughly analogous to DHCP. The idea being that if you have a DTN capable device, a phone or a computer that is equipped with this DNAC, then that when you start up a node, when you insert this device into the network, it can establish its own network identity. It can detect its own lower level communication resources. It can insert itself into the topology of the network, and it can form pathways for secure communication through the network automatically without somebody having to type a lot of things in. So we have some support for this concept in existing work. I'll talk about three sort of classes of supporting infrastructure that I think will help make this DNAC idea feasible. One is that we, years and years ago, and we've had it for a long time now, a standardized neighbor discovery protocol has existed, which enables a node to discover one or more existing topologically adjacent neighboring nodes. And it does that by listening for beacon tones on some general medium that everything in the network is supposed to have access to. Currently, there's a prototype protocol for this, IPND. There's a draft, internet draft for it that's been out for many years. It's been implemented in a number of DTN implementations, and it's based on the periodic broadcast of beacons over UDP broadcast. But you can easily imagine using an RF system or something along those lines as an alternative to that. The discovery of a neighbor enables the first little bit of knowledge of the topology of the network to be communicated to the new node. It also enables discovery of at least one underlying communication channel, so that the node now can exchange the DTN bundles with at least one other node in the network once that neighbor discovery has happened. The second level of infrastructure here is public key infrastructure. Delay-tolerant public key infrastructure is a difficult problem for a number of reasons. The ordinary sort of PKI system that we use in the internet is not so good because it's based on client server, which is innately non-delay tolerant. We do have a prototype implementation and design and internet draft of something called DTKA, a delay-tolerant key administration system that is based on publish subscribe rather than client server. It establishes a trusted distributed key authority, and there's a multicasting of public keys that DTKA relies on that enables signatures and encryption to be implemented using the bundle protocol security blocks and defined for the bundle protocol throughout the network. And then the third element doesn't quite exist yet. There's been a lot of research in it. We don't yet have a solid prototype, but there have been experiments that are very promising, and that is a standardized hierarchical grouping system to locate each node inside a bounded region of network topology, roughly analogous to autonomous regions in the internet, very roughly. The regions are one-for-one with contact plans. That is to say, if a region is a set of nodes, then the contact plan that corresponds to that region is the set of all contacts that are planned between nodes within that region and no others. That means that if the size of a region is kept to a small number, if there are 30 odd or maybe up to 60 nodes in a region, the contact plan is going to be limited. It's going to be 100 or 200 contacts, which is something that you can reasonably search with Dijkstra searches in contact graph routing. What makes this scale up, we think, is that if these regions nest, if they are organized in a hierarchical fashion, then you don't really need a central database of which regions can talk to which other regions. Every region just knows that it can, every node knows that it can talk to everything else that's in its own region, and it can talk to a passageway node that is able to talk to things in the region that encompasses that region. And just by way of an illustration, and I won't try to go into this because it's a whole topic in itself, but you can, let's see, is there a pointer on here? Maybe. Is that where, yeah. You can imagine that if you've got a node in here and it needs to talk to a node over here, it can discover a way of talking to, well, it's not in my region here, so I'll ask my passageway to the outer region. The outer region says, oh, it's not in here. I'll ask this guy. This guy says, oh, it's not in here, but this guy might know. And eventually it percolates down, and the propagation of probe messages that discover the topology of the network automatically results in all of the passageway nodes learning which nodes they can convey bundles to and which ones they can't, so that subsequent communication from this node to this node follows a well-established path that doesn't have to be created manually. It just discovered automatically by the operation of the network. So, given all that infrastructure, here's what we're proposing we might be able to do by way of delay-tolerant network auto-configuration. And it's, I think there are 6 steps in what I've written up here. The first step is the new node needs to compute its own identity, which is in the spaceflight DTN world anyway, that would be a new node number. And there are a number of ways you can imagine doing that. One possibility might be that you can imagine that every node in the network maybe has an Ethernet interface to talk to other nodes on the spacecraft bus or other nodes in the ground station. And in that case, maybe that Ethernet address can be embedded in some, you can have some function of that Ethernet address that becomes a unique identifying node within the entire network, and the node can discover that itself. Another possibility might be some combination of the current time and some sort of coordinates in a location in some common coordinate system. And there are a number of other things that we can explore for ways to select a node number that is known to be unique, and have each node discover that itself. Assuming that we can do that, the new node can compute its own private, a public-private key pair. That's a straightforward thing. It's computationally intensive, but you only have to do it once, or very rarely. Maybe you roll over your keys every I don't know, year or something, but you shouldn't have to do it very often. The private key from this computation is stored locally at this new node. The public key is made available for publication. We can't publish it yet because we don't have anybody to talk to, but it's going to be directed to other entities so that they can encrypt things in that public key, which only this key can decrypt using its private key. The third step, the new node initiates operation of this neighbor discovery protocol. And so now it's listening for a neighbor, something else in the network, some other node that is topologically adjacent to it, so that it can communicate with directly. And until it finds that other neighbor, well, it's not going to be in the network. You know, it's like it can't insert itself into the network until it finds at least one other neighboring node. And so it assumes that it's the only node in existence, that it's the only node in region 1, the universe node, and it's going to change its mind when it discovers another node, but that might happen right away, or it might not happen for some time. Eventually, the new node discovers its first neighbor, and that first neighbor in this context would be termed the new node's sponsor node, because that new neighboring node that is already part of the network is going to vouch for the new node to the rest of the network. The new node uses the newly identified common knowledge communication channel between itself and the neighbor to pass its own node number and its own public key, possibly some other credentials. We haven't worked all that out yet, to the sponsor node. And the sponsor node likewise passes its node number and its public key and some credentials perhaps back to the new node. The two nodes then, by some process we haven't yet worked out completely yet, verify each other's authenticity using some sort of credentials. Maybe that's something that's pre-placed on every vehicle, for example. But one way or another, the nodes determine that each one is authentic enough to proceed with the rest of the integration process. When that happens, the sponsor node tells the new node, here is your home region. Your home region is the same as my home region. You are now in my region. And the passageway node to the encompassing region for our region is this node XYZ. And here's the contact plan for this region that you have now entered. Now, there are no contacts with you yet. We need to work those out. We have discovered a contact, and that's fine, and we can schedule some contacts in the future. But for now, what I'm passing to you is, here's the contact plan for all the contacts among all nodes within your new home region. So if you need to talk to somebody in your home region, here's the plan you can use to figure the route for those bundles. The sponsor node then multicasts to all members of this home region a signed contact plan update message that inserts the new node into the contact plan. This is a registration contact which just basically says this node exists. It's a sort of a dummy contact. The start time is at the end of time, and the end time is like a second after that. But it's enough to insert it into the contact plan so that it's part of the region. And the sponsor node also multicasts to the network's distributed public key authority the signed assertion message asserting the public key of this new node. The public key authority then can include the new node's node number and public key in a message that it multicasts to everybody in the network who's interested in public keys and in a bulletin. And there's a mechanism for doing that in a trustworthy fashion that we think is survivable against natural disasters and lots of different kinds of attacks. The new node then sends a probe bundle to node 0, the non-existent node. The probe bundle is passed to the passageway from the new node's home region to its outer region, to its encompassing region, and it's forwarded from there to all the other regions in the network. As that bundle is forwarded, it's not going to get anywhere because it's destined for a node that doesn't exist. But in the course of forwarding this probe bundle through the network, every passageway node in the network learns where in the network bundles coming from or going to this new node, what passageway to go through to exchange those bundles. And so the new node's location within the network is automatically communicated to all of the passageway nodes in the network, and thereby the new node becomes reachable from every node in the network. And this is all done automatically. So that's the summary slide for all of this discussion. Is we think that this general approach will enable delay-tolerant networks to scale up to quite large sizes, thousands, maybe millions of nodes, by leveraging hierarchical interregional routing and the automated self-configuration of new nodes that doesn't require hands-on management from network operators. And that's the end of my slides. Thank you very much.
Any questions?
So my question is, as soon as we get to the part of this process where there is a new node and a sponsor node, it is now asymmetric. So it makes sense if there's one node that is part of a larger network and one node that's just brand new off on its own. It's pretty obvious which should be which. But if you have two sort of established networks that wander into each other, how do we decide which one is going to play the part of the new node and which one is going to play the part of the sponsor?
That's a really good question, and we've explored that question to some degree, but we're still early enough in the process of working out the details of hierarchical interregional routing we don't really have an answer yet. We know the key principle here is that it's important for nodes strictly to nest. So if there can be two nodes, for regions strictly to nest. So if there are two regions that come in contact with each other, they should come into contact in the sense that the passageways into those regions from the encompassing region come into contact with each other. And if that principle is preserved, then the architecture is sustained, and the math of it all, I think, works properly. But it's a really good question. Something that came to me as I was talking about it was, oh, what if the new node, what if the first node it discovers is another new node, and neither one of them has anything? And that's another point that we're gonna have to figure out a way to make that work. I think these are questions that we can resolve within the context of this architecture, but they're not resolved yet.
So what happens if a node that's an intermediate node disappears for a while and then comes back? So that's going to be the case like if you have airplanes flying in the skies.
Can you speak up? I'm sorry.
So if you have like airplane, it's going to be the case. Sometimes it's just not going to hear the signal.
Well, let's see, the loss of communication to a node that is a transient loss is something that delay-tolerant networking expects, right? That's built into the architecture. If it's an expected loss of connectivity, that should be reflected in the contact plan. If it's an unexpected loss of connectivity, that is a contact that you expect to have happen and it fails, then communication with that node is going to fail for whatever reason, and the reliability mechanisms for retransmission of lost data will start to kick in and say, oh, I'm trying to send to this guy, I can't send to him. At some point, that will raise a network anomaly, and then the question becomes, how do we deal with network anomalies? In the near term, network topology anomalies are going to be things that network managers are going to address manually. In the long term, yeah, something is going to need to be aware of those kinds of problems and make repairs to the contact plans for the network to account for that anomaly. We're not yet anywhere near being able to automate that, but it's clearly a capability that's going to be needed.
Anybody else?
Okay.
Okay, great. Thank you.
Thanks.